Now we'll look at the syscall boundary, and that's the boundary that's right here that separates the user processes from the kernel and capsules. And the user processes have to cross over this boundary to be able to access IOs such as serial ports, and if there's any, let's say, speakers or other types of hardware functionality on the embedded board. For this interaction between the processes and kernels, it can be divided into roughly two categories. One is administrative, and that's going to be things like memory management, and the other are capsule specific. So that's having to cross over to be able to use the serial capsules, alarms, timers, things like that. To do this, to cross over this boundary, the syscalls have to invoke traps to the kernel, so interrupts, which means that it's not that fast and want to be able to minimize that as much as possible. This also brings up the way that the communication goes back and forth, so how the kernel notifies the process that something's done or it's ready for something, and that will bring up for that programming paradigm asynchronous versus synchronous. It's also going to bring up the difference between the application program interface, that the functionality that's defined, versus the application binary interface, which is how that functionality is implemented on specific hardware, such as the ARM processors or RISC-V processes. Now, to look at an example of how this may play out, can go to an example of the process interaction with capsules. So for this example, we're going to have a user process play 10 seconds of music on a speaker. And note, the way I'm showing this wouldn't be a very good way to do it because I'm going to only show one buffer. You would normally want to use two or more buffers to be able to account for any possible delays so that there aren't delays. But for this example, just keep it at one buffer. The first thing for the buffer, the first thing for playing the music, to play the music, is that audio buffer in the user process. So the user process wants to be able to tell the kernel or capsule on the kernel, hey, I want you to take this buffer of audio data and play it out the hardware speaker. So it's going to need to create a buffer of memory in the process space that it can access. It doesn't need the kernel to be able to write to it, so it's not a buffer that needs to have communication back and forth as far as the kernel writing information on that buffer. So this buffer can be read-only allow, which means that the kernel just needs to be able to only read it. It doesn't have to worry about writing to it. So we create a buffer with 1 second of music. And then you're going to need to be able to set up some functionality so that there can be continuous communication with the kernel, because we're going to play more than 1 second. We'll play 10 seconds. So there's going to be need for multiple interactions. And the way to do that is through callbacks. And we'll get into callbacks a little more later on. But what the basic idea is after creating that buffer is for the user process to subscribe to the callback, and that's done by registering a callback to play the next second of music. So that what will happen will be when the kernel has played that second, it can then tell the user process, hey, I'm done, I'm ready for the next second of music. And so that callback that the kernel calls is registered by that user process. And then once this is set up, the process can say, all right, start playing that second of music. And that'll be a command, and it'll issue that command to play the audio. And so in that, once that command is issued, then the user process is going to need to wait around. So these commands in Tock, the user process says, start playing that second of music, and that command returns back quickly to the user process. So then the user process can do something like, oh, I'm going to start getting ready to give the kernel the next second of music. So it can work, and at some point it's going to need to yield to the process because this is a single-threaded application or whole system. So it's going to need to yield to the kernel and then say, are you done? Are you, ready? Should that callback that I registered with you, should you call that callback? And if so, it will copy in. So if that callback gets called, it'll copy in that next second of audio. So it'll update the buffer. The user process will update the buffer. Then it'll issue a command to start playing that second of music. And once it's actually done, then the user process can remove the buffers. It can then clean up the functionality that it created to have those callbacks and then move on. So this was using a few different functions with was the read-only allow to set up the buffer. The user called the subscribe to give the kernel a function that it could call back on, and then it used the command syscall, and it also used the yield syscall. But that's not all the syscalls. If we look at all of the syscalls, which is here, so for all of these syscalls, there's a few more. There's what we saw was the command where the driver, the user process asks the driver capsule to do something, play the audio. It's made up of when it goes to access or ask the capsule to do something, it identifies which capsule through a driver number and what command, like play audio, stop audio, with a command number. And then there's also two other 32-bit arguments that it could use or not. But these are the two primary ones of the driver number and the command number. And this is synchronous, meaning that this must happen quickly. So the user process calls the command, the kernel must do something with it and quickly return back. The read-only allow we saw is how the user process shares user memory with the capsule or kernel. If the kernel needed to also write values, let's say there's some serial network communication where the user process is sending data and then it wants to receive data from somewhere else. So in that case, the kernel would need to write the data it's receiving, so using the read-write-allow. And the kernel can then read from or write to that buffer until the process revokes access. So it's the process that can revoke access. And after sharing, that process should not use that buffer region until the kernel returns it to avoid race conditions. So in this case, after the sharing, the process should do other things but not write again to that region because the kernel owns it until the process has had the kernel release it. There's also the subscribe, which the user process can call to register an up call, which is that user space callback, so that when the driver finishes something, that driver capsule, let's say it's finished playing that second of audio, it's gotten the packet and needs to let the user process know about it, it can call that callback to say, hey, this event occurred. There's also a few administrative syscalls, such as the yield that we saw, where it's blocking, that it can say, the user process can say, okay, I'm done. I'm just now only waiting for you to finish this up, and then it can give control back to the kernel. That way, if there's other processes running, the kernel can run those other processes. There's also yields where it's not blocking too. It's just basically checking to see if the event is ready. There's also memory management operations, And this is primarily concerned with setting up the process's heap and stack allocation to be able to do increasing it, to be able to see how much memory the process is using. And finally, there's exit, and this allows for the safe exit of a process and freeing the resources, and it's also used when a process is needed to restart. So next, we'll look at how you actually, when using the syscalls, what is going on in the Rust code. Here is user-processed Rust code from the libtock rs library that lights up LEDs in a pattern. And the code in main gets the total count of LEDs in the pattern and then loops through them and will light the set a pattern for the LEDs and keep that pattern lit for 1/4 of a second. And then it will just keep looping through all the LEDs. So in this code, the sleep4 calls some of the Syscall API. And the way this function works is that it first, based on the time in seconds or milliseconds, so 250 milliseconds, it converts that to a time that the microcontroller can use, which is in ticks. So it gets the frequency of the microcontroller and then converts that to the number of ticks for the hardware timer to count for that 250 microseconds or milliseconds. And then it's going to set up a callback. So the basic idea is to take the time, set an alarm that the kernel capsule will use, and then when that alarm triggers, it will trigger a callback function to the user process. And so that callback function to the user process is this called, that will be called, and then it's going to use the subscribe and command API from Syscall. And so what it does in this closure is it takes the subscribe, so it calls the subscribe API, so over that boundary, giving the driver number for the alarm driver, and then gives the callback function. So this is what will be, when it's called, what will be filled in for the return values, and then also the subscribe argument. And then it actually initiates the command to start the timer with the command function. So again, that alarm driver number, and then the number of ticks for the command. It will then loop and wait for that callback to occur. So it will yield, and that means that the user process will give over control to the kernel, and then the kernel can call other processes. When a callback occurs, then this will return, and this will then check that. So the reason it needs to check that is because there could be multiple subscribed callbacks for the process. So just because the yield wait returned, you don't know if it was for this callback for the timer. It could be something else that the process is doing. So it validates that by looking at the cell of the reference and then returning that back if it was this particular callback for the timer. This is also enclosed in this shared scope, which is a kind of a helper function that will pass some defaults to make sure that the calls can be safely made to the kernel. Now, with this code, if we look a little more, take a step back and look at how this is interacting, the code in general interacts with the kernel. between the user process and capsule. The basic flow for the command, such as the command for setting the alarm, is that the process will call that syscall command. Then there's that trap or hardware exception trap, the interrupt, so that the kernel takes over. What happens in the kernel is it gets that command number, and the driver number, and it calls the do process, which actually will then route through with based on the trap call of what syscall was made, what to do. And then for the particular syscall driver, it will call that capsule, so it could be the alarm capsule, and then it would call the command functionality based on what that command was. Once that's done, because the commands need to operate quickly, and they're basically synchronous, is that's quickly handled. It maybe sets a flag, and then it returns back a value with the set syscall return value, which goes back to the process, and then the process can do other things. So if we then look, so we talked about the command, we've talked about subscribe. If we look at the other part of that example with the sound, there was setting up the buffers, and you had the allow of read-only and read-write. And if you take just a quick look at what's going on inside the kernel as far as Rust data structures associated with that for that sharing memory. So on the kernel side of that allow buffer, you can see just looking at some of the data structures that's involved. So for the read-only process buffer, there's a couple parts to that. So it's a struct, and it wants a pointer to that buffer in memory that's going to be passed from the process, and in our example had the sound data, the audio data, the size of that buffer, and then also the ID of that process. Now what it does is you see this is a pointer to somewhere in memory, and pointers can be unsafe. So because this is going to be this function new will be creating this data structure with possibly unsafe data. That's why there's unsafe right here. But once that's then created, then the kernel can use that. So this part needs to be carefully done to make sure that something bad, such as a null pointer exception, doesn't occur. But this creates that struct that has all the information that's used in the kernel. And then when the kernel needs to, let's say it would need to pass values back, if there's a passing of data from the kernel to the user boundary, that it consumes the data. That way there can't be a simultaneous conflict with the memory of the pointer of the process and the kernel being able to try to access memory at the same time. And this is the file if you want to look at the code, the rest of the code in there. And in future talks we'll get into more about what's happening right here. The syscall, so we've looked at the syscall functions, and just to kind of see the flow of the implementation just generally with the Rust traits and types. So the traits that kind of are the interfaces, the API that define the functionality, and then the types of data such as structures or enums. To learn more about this, there's a few different kinds that interact between the user process if you're using the libtock rs repository and the kernel side. So the couple traits of interest are the syscalls, which allows for the safe app API, and then also for setting the registers that actually are used when there's the triggering of the interrupt, that's the actual data that crosses over the boundary. Is what's the data that's in the registers, such as like with the command API, where the command API sets the driver, who the driver is in one register, and then in the other registers it could be the command and then a couple of arguments. That would be defined by these traits. The data structures that would be involved would be for the actual calling, the Tock syscalls, and then also for when there is the return from the command from the kernel that represents the registers. That would be the command return. So you can look at these in the libtock.rs to learn more about that. At this boundary layer that's going across would be, depending on whether it's an ARM architecture or a RISC-V architecture, there's going to be different register types filled, and then this information is then in the registers passed across. On the Tock kernel side, so down here, a couple of interesting traits and data types would be the Syscall class that has the number in there of the driver or of the syscall, and then also the decoded syscall request. And then when it's returning back, this command return is not the same data type as this command return, but it's used functionally to the same as far as to return the command values back to the caller, which happens to be in this case the libtock.rs. Although this could be a C, again this could be a C or some other app. And then there's also the syscall return, which is another type. So you can look in the code to learn more about these, but we'll see more of these as we go through this. So we've looked at some Rust code for programming the embedded system and using Tock. Just generally, to take a step back on the programming side of the user processes, there's a lot of interaction with some form of asynchronous technique, and that in Tock's case is callbacks normally, and that is through the yield and subscribe. So subscribe to be able to set what functions that the user wants called back, and then the yield is waiting for those to occur. This is actually pretty similar to JavaScript because most of the embedded systems are all single core, and Tock's single threaded. So one can learn a lot from there, and we'll actually see some asynchronous code that would be something that could be familiar in the JavaScript world. And a lot of, with just in general with this programming of user processes, there's a lot of setting up, doing something, and then waiting around for I/O to complete. And so a event loop is a common coding structure. The question is with embedded, especially because it tries to be as low power as possible, is how do you efficiently set up and run this event loop and not just waste cycles while waiting around. That can be illustrated here when looking at the different types of coding between what's known as synchronous and then asynchronous coding. So an example of synchronous coding for a single-threaded system is, let's say you want to transfer a file and you want to send that file over a network. One way to do it is, if this is the active thread running, it could, for the file transfer application, send some data to the network stack to then send across there. And then while the network stack is sending the data, it can just sit there and wait. And then when the network stack is done, that thread returns back to this file transfer application and it continue working, could then send more data. But there's this time here while waiting for a response where really nothing's happening because it's just waiting around here for that data to complete. It would be nice to actually do something here for that thread. So another option is what's known as asynchronous technique, where the file transfer application says, hey, network stack, send some data. Then while the hardware, so in a way the hardware is acting as another thread sending data, but while that's occurring, the file transfer application can continue working while it's waiting for the hardware to finish, do something, and then when the network stack finishes, it can notify, oh, hey, I'm done, and the file transfer application, if it wants, it could then send more data across the network stack. So basically the file transfer application can do things while the network stack is sending data out of its hardware buffer, and then just get notified from hardware about when it's done and ready to continue working. Two of the common patterns to implement asynchronous techniques are either with callbacks or it's known as async await. And callbacks are nice because they're simple, minimum overhead. Saw that earlier with the example of the alarm timer. They're efficient for single, straightforward asynchronous operations where you're just like waiting for a timer to complete and then you're going to go on about your business. One of the issues though with them is that errors have to be passed through each callback. So if you have a callback and there's an error, let's say it's not able to send the data and it passes back an error message about that, that's going to have to be passed back and handled in the callback. The other point of concern is that when there's multiple steps, it's sending data, then doing something else asynchronously, that you have to start nesting callbacks, and that becomes rather complex. It can be difficult to debug, and it's often known as callback hell. In the other design pattern, which is sometimes used with JavaScript, it's also used in Rust with some different frameworks like Tokyo, is called async await. Here, the code looks synchronous. We'll see an example in the next slide of this. So it's very linear. There's not a lot of nesting like there are with callbacks, but you have to add to the language itself with async commands or keywords like async and await statements. And what it's doing is it's actually creating an event loop behind the scenes. So here with callbacks, they can be nested and complex, but you can pretty much see everything that's going on. With async await, there's state machines and event loops being built behind the scenes that you're not seeing, which can make things a little more difficult to debug. And plus, where it can get really tricky is mixing it with synchronous code, which you can cause a lot of problems. And in Rust, because it'll catch a lot of those, it can make some weird compiler errors that you have to really reason through. So Tock currently uses callback techniques because of that simplicity. If you look on the Tock repository, you can see that there's open issues that are investigating async await to use that. If we look at these two techniques to see what the code looks like, this is more pseudocode, can do a comparison. So synchronous with blocking with kind of a straightforward is, let's say we want to be able to read a sensor. You could read the sensor, then wait till it's done. This would be like that first pattern of where with the slide we're looking at sending data out of the network hardware and then just sat there and waited in the network part of the code until it was done. So read the sensor, wait until it's done, read the sensor value, or send that sensor value over the network to another device, wait until it's done, log if the value was sent, and then do independent calculations. So there's a lot of wasted time in this waiting until it's done. The callback framework resolves that by having a read sensor callback that's called when the sensor value is read to pass it through. But because that sensor value is going to be going somewhere to over the network which will have its own callback, you have to start nesting callbacks. And so this would read the sensor, then you'd have to nest that with sending it to the network, and then that would have to be nested with logging the result. But in the meantime, while this is doing that, you can do your do calculation. Now, ideally would want to put a yield with a no wait inside, so that when this is occurring in the single-threaded kernel, that while you're doing the application, calling that yield no wait to then allow it to transition from once the sensor's read to sending to the network, so that those callbacks could execute. If we compare that to the async await, we have that more linear flow. So reading the sensor value and then await it till it's done. Sending the sensor value, taking the sensor value and then sending it across the network, but we're not awaiting that yet. And this await doesn't mean that it's just like the synchronous code where it's going to stall out, but actually it will go into the that event loop. It'll be using that event loop to then check the values. The send result is then combined with your do calculation, where you'd have to make that, you're taking, could be synchronous code and wrapping it inside an async function, and then trying to join the two and awaiting. So there could be some difficulties in actually implementing this to debug. So it's just something to keep in mind about thinking through how this works with the async framework. It does look more linear than the callback framework, but they each have their own challenges associated with it. And when these are actually running, and when the data is being communicated between the user process and the kernel, we looked at the API, so the Syscall API, and we didn't really talk a whole lot about the application binary interface. So we looked at the API of the subscribe, of the command, of the allow, read only, but not what the ABI is. And the ABI is the actual binary implementation of that binary interface on the specific hardware. So you can think of, like with the API, that this is just how the conversation goes, such as send the command, or I want to subscribe to this function. And then the ABI is more of that wiring and voltage levels of the conversation. So where the language or the words, the wiring and voltage levels are more the maybe the phonemes or the actual sounds. And then for an example of, like, for the LED capsule I looked at, we go like, oh, please toggle LED 0. And then the ABI is setting a specific register value and then executing a hardware specific ARM or RISC-V specific interrupt call. And while this is more of a logical interface in the source code, this is a very binary interface. And while developers, for example, with the libtock RS are writing this, the compiler, when it's compiled down to the ones and zeros, it's doing this. So source code that we edit with would be the API, and then the compiler would be that ABI. And then if you have to make changes, just recompile it at the source level, make changes there. But the ABI is a contract on that process, so this can cause big problems if you're going to break compatibility. And actually, in some languages like C++, it's been a real problem source of do you break compatibility to get future improvements, where it's a lot harder to break compatibility there than with the API. And then this is some examples. For the in the Tock book, you can see, this is from the Tock book, can see that with the ARM Cortex-M versus the RISC-V, you have different Syscall registers being used, and then also different Syscall, the way that class ID is, it's different. And then also with the up call, so those callbacks, how that's handled with which registers. So the just kind of like I tend to think of it as API is what you say, while the ABI is how you say it in the particular processor's language. So to wrap this up, just to give an example with that API and ABI, you have here for the Syscall class, so the yield subscribe command, that API that we've seen with that number, and if we look at one of them in particular, the command, we can see that the arguments, so for the command with the LED, that it starts with the driver number and then the command number, so turn on, turn off. Here are the different commands, like command number 0 is turn on, or how many LEDs are supported. Command 1 is to turn on LED. Command 2, if send a 2 there, is turn off. And the ABI is actually setting the register, so putting those values, those registers, particular registers type for that architecture would be the ABI. And then this just shows then the other command setup there for that.